Hello, everyone, and welcome to my presentation about green AI. So before I get started, just a few words about myself. My name is Roy Schwartz. I'm a senior lecturer, or the equivalent of assistant professor at the School of Computer Science at the Hebrew University of Jerusalem. My main field of research is artificial intelligence, and in particular, natural language processing. And I like to study ways to get better understanding of the way our models work and what's going on under the hood, and to reveal the biases in the data set that we use, and more specifically to this talk, how to make AI more sustainable. Now, while I study broadly AI, most of my research is about NLP, so most of the examples I'll be using here are from this domain, though I think most of them generalize beyond that to other fields of AI. Okay, so when we talk about AI today, I think we're seeing groundbreaking results coming out almost on a weekly or even daily basis. I mean, a few years back, we've seen the AI technology beat world champions in games like Go or poker. We can communicate with our phone quite easily nowadays. And most recently, we've seen tools that can help us generate images based on any given prompt, or most recently, chatbots that communicate with us quite proficiently and reach very impressive results. Now, this is, again, a very exciting time to be doing AI research and working with this technology, but something that's perhaps not as discussed as the amazing results that we're seeing is one of the major contributing factors to this success, which is the scaling of these models. So what we're seeing here is the graph showing the state-of-the-art NLP models over the last 4 or 5 years, starting from Elmo in 2018 all the way to Palm that came out a few months ago. And on the y-axis, we see the model size, which is the number of parameters on a logarithmic scale. And on the x-axis, again, we see the year. And what we've seen is an exponential growth of about 5,000x in 4 years. Now, this trend is, again, one of the driving forces of AI. I mean, one of the key elements of deep learning, which allows it to be so successful, is that it scales so well. But at the same time, it raises a few problems that I will be discussing here in this talk. So this talk is titled Green AI, which is the name of a paper that I wrote with a bunch of colleagues at the Allen Institute for AI, where I worked previously. And in this paper, we talked about the different problems that arise by simply improving models by scaling them, problems such as lack of inclusiveness and potential environmental impact. And I will discuss these two issues in this talk. And then we proposed an alternative, which we titled Green AI, which is based on two leading principles. One is enhancing the reporting of computational budgets, and the other is promoting efficiency as a core evaluation for AI. Now, again, today I'll be briefly mentioning the first component of reporting throughout the talk, and talk a little bit about efficiency and recent approaches that seem to be working pretty well for this to promote this agenda. So to get started, let's start by diving into the problems with scaling. And the first one you can, I think many of the people attending this can relate to, is the lack of inclusiveness in generating state-of-the-art results. Because models are becoming so much larger and so much computationally expensive, they require simply lots of money to run them and to train them and even to use them in practice. And here are some numbers. BERT, which was one of the pioneer models in NLP, one of the largest models at the time, was trained on 16 cloud TPUs for 4 days. I still remember back at the time, this seems like quite an expensive operation that no one could afford to reproduce. But only a few months later came out Roberta, which was trained on 1,000 GPUs for approximately 1 day. Again, a jump of about 2 or 3 orders of magnitude. And Palm, which I mentioned earlier, was trained on 6,000 TPUs for 50 days and plus 3,000 TPUs for 15 days. Again, seeing this jump, and not many institutions around the world, maybe a handful, can afford to run these training procedures. And obviously, this leaves out the 99% of the community potentially out of the the ability to influence what is the state of the art. Now, you might be wondering why I jumped from 2019 to 2022 in this slide, and this is simply because many of the models that came out in between did not bother reporting this information, which leads me back first to my first point about how can we improve the situation where scaling is so dominant. And I think the first thing we need to notice is that we need better reporting. We need papers that clearly describe the procedure and describe how much compute went into generating the given scientific results. Now, looking at going back to the first slide I showed earlier about scaling, you can also see to look at which institutions generate these results, and you see the same names over and over again. Huge tech companies such as Google, Nvidia, OpenAI, which is powered by Microsoft, and Huawei are the names that we see here. We see the same names over and over, and not many small startups, not many academic institutes. And again, this is a very, very high bar for entering this competition, or if you want to call it, of generating strong models nowadays in AI. So this was the first problem with scaling, which was inclusiveness. Now let's talk a little bit about the second problem that I mentioned, which is the environmental aspect. What we're seeing here is a table from a paper from Emma Strubel and her colleagues at the University of Massachusetts, a seminal paper that first studied the environmental impact of state-of-the-art NLP models. And what they showed is that if you take the most expensive operation that existed at the time, and this was around 2018 or 2019, and training a model with neural architecture search, and compare it to everyday operations such as such as driving your car for the amount of carbon that is emitted by a single car in the course of its lifetime, you see that training our largest model at the time was equivalent to about 5 cars in the amount of carbon that they contribute. And again, this I think was a very surprising results, because at the time it wasn't considered. Not many people thought about the problem of the environmental impact of AI in general. And so going back to this result, one might wonder whether this is really is this a high price to pay? Maybe, I mean, if we're trying to push the state of the art in AI, maybe this is a reasonable price to pay. And again, I think this is a very important and interesting question to be asking, whether AI is really creating an environmental problem. And several people have tried to address this question. And one of the organizations that tried to do that was Google. And they wrote a blog post about a year ago where they stated that the answer to this question is no. They titled their blog post "Good News about the Carbon Footprint of Machine Learning Training." And what they were trying to argue is that the paper that I just mentioned had wrong estimation because they didn't take into account information about how these models were trained, and they were off by between 1 and 2 orders of magnitude related to the real cost that was required to generate these results. Now, why did these people, the Strubel et al., make these mistakes? Because they didn't have this information, because it wasn't available in the original papers, which goes back to the same point. We need better reporting of our energetic cost, of our carbon cost, and so on and so forth. Now, taking Google answer, we also try to address this question. When we say we, I mean myself and partners in Microsoft Azure, the Green Software Foundation, the Allen Institute for AI, and other organizations. And we try to basically measure how much different AI operation that are run on Microsoft Azure the cloud service, how much CO2 do they emit. And we generated this graph that on the y-axis, you see the amount of carbon being released by different operation. And on the x-axis, you see different models in both NLP and computer vision. And on the right-hand side, you see everyday operations, the amount of carbon that everyday operations emit. Now, let's zoom in a little bit and try to see what we're seeing here. So this is one example, the training a transformer model, a standard NLP model with 6 billion parameters, which is pretty big, but definitely not the biggest that we have. This consumes about 10 million CO2 grams, which is the equivalent of a single home in the US, the amount of energy it requires, or the amount of carbon it emits in a single year. So again, I mean, this is I don't think this gives an answer whether this is a real problem or not. Now we're talking about one model, which is equivalent to one home, and I think that this is interesting because the experiment that I just described was very far from being the largest experiment that people are running nowadays. Now we're talking about models that consume 2 or 3 or even 4 orders of magnitude more carbon. So basically, the largest experiment we have maybe omits on the order of magnitude the same amount of carbon as a whole neighborhood or perhaps a small town would in a single year. Again, is this expensive? Is it not? I mean, I think the main point here is to be aware of this, try to do the best we can to reduce these costs. And it's important to remember, for instance, that these experiments are the most expensive experiments that we have, and they're typically run very few times. So maybe these are very expensive costs, but maybe because they run just once a handful of time every year, maybe it's fine to invest this amount of carbon. But I mean, I think where far less information exists is about normal experiments, quote unquote. I mean, just training a much smaller model on your laptop, on your university server. I think these experiments are maybe run maybe hundreds or even thousands of times a day on the one hand, but they are much cheaper on the other hand, so it's much harder to get an accurate estimate of how much carbon do they actually emit. And I think even more so, we can talk about inference operations, basically taking a trained model and running it on your example. These operations are far cheaper. They're really, really cheap compared to training, especially pre-training, the most expensive ones that we've talked about. But on the other hand, these are run maybe billions of times a day. If you think about your favorite search engine or your content recommendation, whether it's Facebook or TikTok or Twitter or whatever, AI is running under the hood and billions of times a day, even more frequent. So how much do these contribute to the carbon cost of AI? And indeed, 80 to 90% of the AI computation, based on some estimates, is spent on inference. So again, I think the overall conclusion, it goes back to the same point that I was talking about so far, that we need better reporting. We need better ways to measure how much carbon is being emitted on the various aspects, both on the most expensive experiments, but also on regular experiments and even on inference experiments. Sorry about that. So zooming out a little bit. So we've talked about Red AI, the process of generating results by increasing the scale of models. We talked about the problem of inclusiveness and the problem of the environment, and we've talked about reporting as a potential solution to these problems. And I want to focus in the rest of this talk on the second proposal that we talk about when we talk about green AI, which is promoting efficiency as a core evaluation for AI. So when we talk about efficiency, maybe many of the people attending this talk might be from related to a computer science background, and I can only assume that many people here, like myself, kind of wonder why is this even something worth mentioning? I mean, in computer science, one of the basic operations that we talk about is starting the very first classes that we take is about efficiency. How do we sort lists efficiently? How do we do different algorithms efficiently? This is a core thing in any computer science discipline. But at the same time, AI may be a bit behaving a bit differently, because the main focus of this field is trying to push the limits of what AI systems can do. And indeed, we've seen that there's a much larger push towards better accuracy compared to better efficiency. And to kind of quantify this, we did a small survey of taking 3 state-of-the-art conferences in NLP, computer vision, and general machine learning. And we took a sample of papers and tried to look whether the main contribution of these papers is a more accurate result or more efficient result, or either both of these or some other key result. And we've seen that across all conferences, the main contribution of most papers was about accuracy. So again, I mean, there's and what we're trying to argue is that should be some balance between these. I mean, we want to see more papers trying to reduce the cost of AI, to trying to make things run faster, more efficiently, with consuming less energy, less carbon, and so on and so forth. And myself and another group of people have tried to work hard to both convince the community to put more efforts into this, and also in generating some key results that help reduce the cost of AI, which I want to give you just a little taste of some of the results that my lab has been working on over the last few years. So the first idea I want to talk about is how to do faster training by doing smart filtering of the data. This is work done at the Allen Institute for AI and the University of Washington, led by Swayam-Dipta, and with other colleagues. And the key intuition here is that not all training instances contribute the same to learning. Some of them are easy to learn for the model and therefore don't contribute much, and others are more challenging and perhaps give a better signal for the model. And what we did in this work was we created a sort of a data set map, where what we see here is that different points along this plot represent different training instances. So there's quite a few of them, and without going into too many details, we see different regions that we attribute some of them to be instances that are easy for the model to learn, some that are hard for the model to learn, and others that are ambiguous. In some sense, excuse me, they're not too easy and not too hard in some sense. And after we generated this map, we want to see whether this map results in how does this affect learning. So we did some experiments. The details aren't that important, but we started with the baseline of training the model on the full data set of 100% of the data, and got some results. Excuse me. Then we ran two baselines that only train on 1/3 of the data. Now, when you train on 1/3 of the data, assuming that the number of epochs is fixed, you get training that runs 3 times faster. The math is pretty simple. And the first baseline that we used was a random baseline, basically the one that randomly selects 1/3 of the data and just train on that part. And we see here that this causes quite a substantial drop of about 6.5 points in that task. And then we took the 33% that are most ambiguous, going back to the graph here. The leftmost part, the rightmost part here, we took the 30% that are the rightest to the graph, as you can think of it, and we see that this results in a much higher performance within 1 point of the training on the 100% of the data. And not only that, when we evaluated our models on outer distribution data, which is considered much harder, we saw that training on 1/3 of the most ambiguous examples not only did not lead to worse results, but actually led to better results than training on the full data. So in some sense, we were able to present a method that allows us not only to train faster, but also to generalize better to other types of data. Now, this is one result. The second result I want to highlight is a result that focuses on the transformer model, really the leading method for text representation, but also for vision, speech, combio, and many other fields of AI. And for those of you who are not familiar with the inside works of the transformers, the key component here is that we have, in order to represent some word, this word needs to be a function of all the other words in the document. So in some sense, if you want to represent, think of each of the nodes here in this graph as some sort of representing one word in a document. So the first word is a function of all the other words. The second word is similarly the third word, and all the way through the nth word, which simply gives, if you think of what's the complexity of representing the whole document, we have n words, each of them attending all the other words. So this is n squared in the length of the sentence, and this could be fatal for if we want to represent long sequences such as books, articles, and so on and so forth. So there's a great motivation to try to generate a more efficient variant of transformers that works in a sub-quadratic complexity. So I want to briefly mention one of the efforts that we've made along this line. This is work led by Hao Peng with colleagues from the University of Washington and DeepMind. And the key idea here is to approximate the attention function using random Fourier features. Basically replace this n-squared operation with a more efficient random Fourier-based operation. Now, there are quite a bit of math in the paper that tries to illustrate how we do that. In the interest of time, I won't be getting into this many details, but what we get is a model that runs linearly in the content length, and also the memory requirement, which is another major bottleneck, is also linear in the document length. So to get a sense of how this model performs in practice, the model which we call RFA, you can see here a comparison with various other models that try to do efficient attention. And on the y-axis, we see accuracy, so higher is better. And the x-axis is the relative speed up, basically how much faster is the model. And we see that our model gets the optimal trade-off between speed and accuracy. And similarly, we can also measure the memory efficiency, basically how much memory does the model consume. And again, we get a very good trade-off between accuracy and efficiency. So this is another approach. And the third idea I want to briefly mention here is a method for making inference more efficient. And the key intuition here is similar to the first work that I presented about different instances contributing differently to training. Now I want to see how different instances can be can require different amounts of computation and inference time. So assume that we have a set of models, each of them growing in size. So basically, the different dots here represent different models. Each of them has a different accuracy level on our given task, but also has a different inference time. So basically, the models that are to the right run slower; they take longer to run, and models that are higher are more accurate. So ideally, what we want to do. So if we have this model here that is the most expensive model that we have, but the most accurate one, and this model here is far more accurate, but at the same time more efficient, we would like to run our easy instances, quote unquote, on the efficient method, and our hard instances on the expensive or accurate method. And if we had an oracle that tells us which example can run on which model, we might get some trade-off like this, which something runs almost as accurately as the most accurate model and almost as fast as our fastest model. So without getting into too many details, we built a method that tries to estimate this oracle, and we ran some experiments. Excuse me. And we will consider the results here. So again, what we're seeing here is the list of models and how much we get, but if you only run each models on the entire data set. And we see already that this is a fairly strong baseline. And this point here, for example, runs 3 times faster while being less than 1% of the full model. But we're able to get this trade-off here that if you compare the best baseline that we had here to one of our results, you get a model that runs 5 times faster while being within 1% of the full model. So by better exploiting the different models and running each of them on different examples, we're able to get much better speed accuracy curve compared to our baselines. So I want to conclude this talk here by briefly reiterating the things that I've shown you here today. We've talked about the concept of red AI, which basically means getting better results by scaling our models. We've talked about the problems that it creates, problems of inclusiveness, that not many people can afford to run these experiments. We've talked about the potential environmental impact of larger models that are more expensive and consume much larger amounts of energy. And we've talked about green AI, which is an alternative approach that tries to enhance the reporting of computational budgets, basically being more honest, more open about how much compute is required to generate a given result, and promoting efficiency as a core evaluation measure for AI, basically saying that we want to push approaches that promote efficiency, getting models that run faster, that consume less memory, less energy, less carbon, and so on, and not only models that are more accurate. So with that, I would end, and thank you for your attention, and I'll be happy to take questions.